Section 3.5, limits at infinity. So we're going to take a break from derivatives for a little bit and talk about another feature of a graph that's really important, horizontal asymptotes. If you have a function like this, x cubed plus 6x plus 4 all over x to the fourth plus 1, you can see that this is what's going on in the center of it. But as x approaches a really big number, this graph looks to level off at y equals 0. So if we think about this limit at infinity, so if we think about x approaching infinity, that y value approaches 0. If we look at this side, if the x values get really, really small, as x approaches negative infinity, it looks like the y values approach 0. What that is a horizontal asymptote at y equals 0. And you can see that it's okay for a graph in the center of the graph to cross the horizontal asymptote. A horizontal asymptote is only an asymptote that doesn't get crossed at the ends of the graph. It's called end behavior, the end of the graph. So as x approaches positive infinity or negative infinity, what's going on around 0, that's fine. Your graph can cross the horizontal asymptote. So they're a little bit different than vertical asymptotes in that way. Let's review some pre-calculus ideas. You talked about in pre-calculus if the degree of the numerator of a rational function, remember rational functions are functions that are written as ratios or fractions with an x in the denominator, could have an x in the numerator. If the degree of the numerator, so on this one the degree of the numerator is 4, it's the highest power, is greater than the degree of the denominator. The degree of this denominator is 2. So the degree of the numerator here is greater than the degree of the denominator. There is no horizontal asymptote. This graph looks like this, and it never levels off. As x approaches infinity, this graph continues to go up. It never levels off at any particular y value. Same thing as x approaches negative infinity. This graph will never level off at any particular y value. And you can tell that just from the function by noticing that the degree of the numerator is greater than the degree of the denominator. If the degree of the numerator is equal to the degree of the denominator, so they're both x squared here, then you have a horizontal asymptote, and it's the ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. So this one would be 3 over 1. So this would have a horizontal asymptote of y equals 3. And you can see here, as x approaches infinity to the right, we have a horizontal asymptote at 3. If the degree of the numerator is less than the degree of the denominator, so the denominator has a higher degree, then the horizontal asymptote is always at 0. And you can see this one as x approaches infinity, it's leveling off at 0, and as x approaches negative infinity, it levels off at 0. Let's analyze that with calculus a little bit. A horizontal asymptote is a limit as x approaches infinity and negative infinity. So of course we're going to write it with limit definitions. Limit notation. The line y equals L is a horizontal asymptote if the limit as x approaches negative infinity of that function equals a certain number, or if the limit of the function as x approaches infinity to the right equals a certain number. So if you can find the limit as x approaches infinity of a function, that will be your limit. So let's look at it, not thinking about the degrees anymore, but looking at the calculus of it, the limit of it. The pre-calculus ideas we just talked about are shortcuts, and you can still use them, but I want you to understand the background of it. If r is a rational number, so r could be a fraction, a whole number, a negative, and c is any real number. So we have a whole number up here like 7 or negative 2. Then the limit as x approaches infinity is 0. If you think about what that means, let's look at a simple case like 1 over x. If the denominator is infinity, if it gets bigger and bigger, so our fractions like could be 1/2 and then 1/3 and then 1/4, and then x is getting bigger and bigger, like 1/10 and 1/100th and 1 over 3 million. What is the value of that fraction going to be approaching? It's going to be approaching 0. So even if I squared x or did the third power of x or any other power here, 1 over infinity will always approach 0. The limit of 1 over infinity will always approach 0. Look at this one. If we put infinity on the top, x cubed, infinity cubed, even half of infinity cubed will still be infinity. So that means there's no horizontal asymptote. There's no limit. This function would go up forever or down forever as x approaches infinity. The end behavior just keeps increasing or decreasing. We can look at this to try to find the limit as x approaches infinity. Notice that the degree of the numerator is lower than the degree of the denominator. So using your pre-calc ideas, you should know what's going to happen. But let's do this analytically. We only know the limits of fractions, like this, this kind of fraction. So we want to make everything here a fraction. So we're going to divide each term by the highest power, by x to the highest power. By x to the highest power in the denominator. So x to the fourth is our highest power. So we're going to rewrite this and divide each term by x to the fourth, and we'll see what happens. It's legal as long as we divide every single thing by x to the fourth. And we're still going to try to find the limit of that as x approaches infinity. So let's reduce these. That becomes 1 over x. This becomes 6 over x cubed. The next one becomes still the same. Nothing reduces there. This is 1, and then 1 over x to the fourth. So as we take the limit of that as x approaches infinity, so we're going to put infinity in each one of these fractions. This is 1 over infinity, so the limit of that is going to be 0. This is 6 over infinity cubed. The limit of that is going to be 0. This is 4 over infinity to the fourth, so the limit of that's going to be 0. This is 1 plus 1 over infinity. That's going to approach 0. So we get 0 over 1, which is okay. That's 0. So y equals 0 is our horizontal asymptote. It's the answer, it's our limit. The limit here is 0. Did that go along with our pre-calculus idea? If the denominator, or the degree of the numerator is lower than the degree of the denominator, we're going to have a limit of 0, a horizontal asymptote at 0. Now why can't we just plug in infinity, do direct substitution? Remember, I always say try direct substitution first. Well, if we had done that, we'd have infinity cubed plus 6 times infinity plus 4 over infinity to the fourth plus 1. Well, infinity cubed plus 6 more infinities plus 4 is going to be infinity, and infinity to the fourth plus 1 is infinity, and that's an indeterminate form. So that's why we had to divide each indeterminate form. That's why we had to divide each term by x to the highest power, because it gave us individual little fractions that we can find the limit of instead of just infinity over infinity. Here is an example of where you need to use the dividing by the highest power in the denominator. If we just put infinity in the top and the bottom, we'll have infinity over infinity. So direct substitution gives us this indeterminate form. So what's the highest power of x in the denominator? Right now in the denominator we've got x squared inside of an x. That's just looking at the power, which is essentially x. So when we're in the numerator, we're going to divide by x because that's not in a square root. But in the denominator, since that whole denominator is inside the square root, we're going to divide by x squared inside of the square root. Reducing that, we have 3 minus 2 over x, all over the square root of 2 plus 1 over x squared. So taking the limit as x approaches infinity, this is 3 minus 2 over infinity is 0. In the denominator, 2 plus, and then the limit of 1 over infinity is again 0. So we have 3 over the square root of 2. And they might rationalize the denominator by multiplying the top and the bottom by the square root of 2, or they may not. So be able to do it both ways. On the test, I don't care. You can leave it like this if it's not multiple choice. Okay, negative infinity. It's the same idea, but we're using a negative infinity, so we're thinking about where this function goes to the left as x approaches infinity to the left. All right, so thinking about as x approaches infinity to the left, or going to the left, you have to think about what happens when you do a square root of an x squared. You could have two answers, right? Plus and minus. So now we're going to deal with the negative square root of x squared, or negative x. We're going to divide both top and bottom by the negative value, because square roots have two possibilities, right? So 3x over negative x minus 2 over negative x divided by the square root of 2x squared over negative x squared plus 1 over negative x squared. Okay, so that reduces to negative 3 plus 2 over x. And here, I think we want the negative outside. Yeah. Put the negative outside there. No, hang on. All right, sorry about that. So we have x can be two things. X can be positive square root of x squared, or x can be negative square root of x squared. So the positive x is what we're dividing by here and here, but we are dividing by negatives inside of here. So sorry about that. All right, so again, x, when you take the square root of x squared, it can be a positive or a negative. So x will be positive x squared or x will be negative x squared. So 3x over x minus 2 over x divided by 2x squared over negative x squared plus 1 over negative x squared. So we have 3 minus 2 over x, and then here we have negative 2. No, I think we wanted that negative outside. Sorry about that. Still making mistakes. We want this negative outside of here, because you can't have a negative inside the square root. So this negative's outside, right? So we're dividing by negative outside. So there's a negative outside of there. All right, so we have 2x squared over x squared reduces to 2, and 1 over x squared is still 1 over x squared with that negative outside of there. So in the numerator, we take the limit as x approaches infinity. We have 3 minus 0. And in the denominator, we have negative square root of 2 plus 0. So we have 3 over the negative square root of 2, which is negative 3 over square root of 2, or square root of 2 over 2. Multiply the top and bottom by negative square root of 2 over 2, and we get negative 3 square root of 2 over 2. All right, that's a lot of mess for just getting a positive and a negative answer. You could probably just jump right to that positive and negative answer. Sorry about all the craziness there. Make sure that negative's outside, and you'll be good. All right, remember when we talked about the limit of sine x over x as x approaches 0, and that was equal to 1? We did that by the squeeze theorem. So let's look at the limit of sine x over x as x approaches infinity. All right, so thinking about that, this red line in the middle here is sine x over x, okay? And thinking back to this where we wanted x approaching 0, it was x approaching 0, so then our y value was at 1. So the limit as sine x over x approached, the limit of sine x over x as x approaches 0 was 1. But now we're looking at the other end of the graph. What happens to this graph as x approaches infinity? So as x gets bigger and bigger and bigger, what happens to the y values? If we squeeze it between these two functions, the y value you can see is going to approach 0. So here's another theorem you need to memorize, another limit you need to memorize, and we already memorized this one, so don't get the two confused. One is 0 and one is 1, and then we had the 1 minus cosine x over x, and that was limit as x approaches 0, and that was equal to 0. So be careful about what you're approaching and what it's going to equal and what the function is. So those three things you need to make sure you memorize. We already had these two. This is the new one. So if we are asked to find the horizontal asymptotes of f of x equals 6 sine x over x cubed plus 2,